Hello and welcome to another class of ATMO 620. I hope you're all doing well. I hope you enjoyed the microphysics part of the class. And I hope you enjoyed it because today we will start a new direction. Okay, we'll start exploring a new direction. If you remember at the beginning of the class, I said that this class would be concerned with the problem of what could happen to a parcel of air that is, apart from dynamical consideration. So anything that is in dynamics, what could happen? Okay, I hope this makes sense. And at the beginning, if you remember, we said, well, one thing that could happen to a parcel is thermodynamics, one set of processes that affect the behavior of the parcel would be thermodynamics. So thermodynamical transformation, increasing pressure, temperature, and whatnot. And we started talking about that a little bit. We kind of had a refresher of the first and the second principle of thermodynamics, and then we started talking about the fact that parcels of air aren't only made of dry air, which is nitrogen and oxygen and other gases, but although in a smaller concentration. But there's also a gas in the air that is important, which is water vapor. Now, water vapor is present in a much smaller amount compared to other gases. But it can have a tremendous impact on the state of the atmosphere, on the parcel of air. Why is that? Well, because water vapor undergoes phase transitions at temperatures that occur pretty much in normal conditions in different parts of the atmosphere. Okay, oxygen doesn't condense at room temperature or at temperatures that can be achieved anywhere in the atmosphere. Water vapor is kind of in a sweet spot between abundancy and being able to transform itself, if you will. Okay, so it's abundant enough. It's kind of rare enough that it's not the main constituent of the atmosphere, but it is abundant enough that its effects can be felt by a parcel of air. And so then we started talking about what could happen if indeed water vapor undergoes some kind of phase transition. We talked about homogeneous and inhomogeneous nucleation. We talked about freezing. We talked about ice nuclei, ice crystals. We talked about rain and snow and precipitation. Today, I want to start sort of a new direction that is somehow related in the sense that it is still concerned with processes that could happen, that could affect a parcel of air, okay, other than dynamical processes. But it's kind of disjoined from the thermodynamical processes that we considered before. The set of processes that I want to introduce today is the interaction with radiation. Okay, another thing that could happen, and that does happen in the atmosphere regularly, is that air parcels interact with solar radiation, and that has some effect on the air parcels on the atmosphere. Okay, so this is the third and last chapter of this class, and in this chapter we'll be concerned mostly with radiation. Okay. Now, radiation is a bad word in sort of common parlance, if you will. But it's only because I think it's commonly associated to a particular kind of radiation, which I guess in physics you'd call ionizing radiation, meaning radiation that is high energy and that can affect the tissues in your body and therefore, long story short, can give you cancer or leukemia. right? But radiation is not necessarily a bad thing, and it doesn't only have to do with nuclear decay, which is what some of the most dangerous radiation refers to. Okay, and for us, radiation will mean light, will mean electromagnetic waves. Okay, and which we'll introduce in this lecture. A very brief overview of what we will talk about. Sort of the basic things that we will discuss. We will start with some very basic physics, if you will, and we will introduce the Planck function today. We'll talk about local thermodynamic equilibrium, and then we will talk about radiative transfer equation, diffuser approximation, extinction and emission, what these things mean. We'll talk about molecules and some basic spectroscopy of molecules. This will allow us to introduce vibrational and rotational states. And then we will briefly introduce the concept of transmittance. And we'll continue talking about absorption of radiation by atmospheric gases. Okay, this includes the UV absorption and the infrared absorption. We'll talk about heating rates, meaning what effects has the absorption of shortwave or long wave on the atmosphere. Okay, and then in the last part, we'll introduce the greenhouse effect, which you might have heard is playing some role in climate change. And then we'll talk about scattering a little bit, and we'll conclude with radiative feedback, if you will. Okay. The textbook that I am following for this part of the class is this textbook here. Oops, excuse me. Textbook by David Andrews called An Introduction to Atmospheric Physics. And from this textbook, we will be following these particular chapter 1.3, chapter 3, which will be the main, sort of the bulk of what I'll talk about, and chapter 8. Okay. I will be providing lecture notes and such, so you don't have to buy the textbook. For those of you who are interested or kind of need something a little bit more, a little stronger, I'm happy to give you some recommendations on other textbooks that you could be using, something a bit more specific than this one. Okay, so let's start with a very basic question, okay, that kind of serves to illustrate why we are concerned with the interaction between radiation and the atmosphere, okay? And which also illustrates why the atmosphere is important, other than the fact that we need something to breathe, okay? Okay, so, and let's start with a very simple question, which you might have seen before, but a very simple question of how can we determine the temperature of the Earth, okay? Temperature of the Earth is a result of two things. First, some heating tendency, okay? And the heating is provided to the sun, which is very generously providing heating to all of the solar system. And this source of heating is kind of constant, right? Because even though we're circling around the sun, we are always in its orbit. And so the sun is always pumping energy into the atmosphere. And because the temperatures on Earth have reached some kind of an equilibrium, this is sort of debatable given that, given climate change. But, by and large, temperatures are not constantly increasing, right? After 4.5 billion years, if there wasn't something to cool down the Earth, would have a temperature of a bajillion degrees, right? So there has to be something that compensates. And what compensates is the fact that the atmosphere, the Earth, pardon me, is radiating, is redistributing the heat, and it's kind of excuse me, this is hard to say, emitting the heat back to space. Okay, and so the temperature is balanced between two things: the sun that would like to heat us, and the processes that diffuse, or better, radiate this heat away. Okay. If we wanted to use formula, we could imagine that, first of all, we could imagine that we're far enough that the sun rays, even though they are obviously divergent, right, and they come out at an angle from each other, we could assume from simplicity that we're small enough and far enough that the rays that hit us are so close together that they're almost parallel. Okay, that kind of helps us simplify a few things. Okay, and let's say that the sun is emitting with this power, with 1370 watts per meter square. That is not the power with which the sun emits, but it's kind of the power that that reaches us. Okay. Remember, I mean, we're at a certain distance, and so the power that is emitted by the sun decreases with the square root of the distance. So what we get, you know, the power at this point, at the tip of these arrows, is 1,370 watts per meter square. Let's further assume that some of this power is reflected right away. Okay, it won't even be absorbed by the Earth. And this effect is known as albedo. Okay, and the albedo is a measure of how much radiation you're actually absorbing. You know, when you go out and you're wearing a white T-shirt, you feel in a certain way. You don't feel particularly hot. If in the same day you wore a T-shirt made of the same material but black, you'd be a little bit warmer because black absorbs heat a little bit more. It has a different albedo than white. White has a higher albedo, meaning that it reflects, doesn't even want to talk to the heat that is coming in. And so let's assume that 30% of the power that is coming in is just reflected away, no question asked. And so effectively, what is reaching the surface of the planet is the power, the solar power times 1 minus A. Okay. Now, this is the power per unit area. Notice how F is watts per meter square. And so how much is actually, so this is, you could think of this as sort of a density of power. So how much of this actually reaches the Earth? So if that is a density, how much is actually deposited on the Earth? Well, to answer this question, we need to compute the area of the planet, and in particular, we need to compute the area that the sunbeam kind of sees. Okay, not the area of the planet itself, but what the sunbeam sees. And imagine that you're driving into an electricity. No, that's a bad metaphor. That you're driving. Suppose you're running into a pole, okay, or a tree branch, or a tree trunk, whatever. So you're driving again towards a tree. Now the tree, I don't know where to draw it, but I could draw it here. The tree would look something like this, kind of cylindrical, and then here that would be sort of the vegetation, okay. But and again, the trunk is kind of a cylinder. But as you're driving towards it, the tree to you, in front of you, it would look something like this. So what you see in front of you is not a cylinder, it's a rectangle, okay? It's a two-dimensional thing. And this is even clearer if you close one of your eyes and you just look with one eye, then you lose the three-dimensional vision and you'd really see just a rectangle. Same way the sunbeam is traveling towards the Earth. What the sunbeam sees is not a three-dimensional planet. It sees a circle because that's what the Earth looks like as you're approaching it. And so the area that we need to multiply by is the area of the circle. Let's say that the radius of the Earth is r, okay, so that would be pi r e squared, okay, which is exactly what I wrote down here. So this is the heating, okay? Okay, excellent. How much is radiated away? Well, we will talk about this, but essentially the power that is radiated out is sort of F Earth, if you will, is the density, the power density, if you will, goes something like sigma T to the 4 power. Sigma is a constant that is known as Stefan Boltzmann constant. We'll talk about this, but Stefan Boltzmann. Yeah, Boltzmann is the same guy that we saw from the entropy, the person who introduced entropy. He also kind of experimented with radiation because that was kind of a hot topic at the time, pun not intended. So this is kind of the density, and this is the temperature of the Earth. And now, because this is density, we need to compute how much it actually is, and so we need to multiply this by an area. Okay, now, this is the radiation that is emitted by the planet. And so the real density, the real area that we need to consider here is not the cross-section that is seen by a sunbeam, but it's all the surface of the planet, because all the planet is emitting. And so that is 4 pi r squared, which is the area of a circle. I'm sure you'll remember this. So this is the balance equation that we get out of this. And we can just go right ahead and compute what t is. So extract t from this. The pi's simplify out. Interestingly enough, the radius of the Earth also kind of factors out. And so t is just the 4th square root. I'm not sure how you'd say it in English, but f times 1 minus a over sigma. For the albedo, we assumed 30%, which is kind of an average, if you will. Certain areas of the planet have a higher albedo. But anyway, so you do this calculation and you obtain 255 Kelvin degrees, which is minus 0.67 Fahrenheit, which is cold, hence the snowman here. The real actual temperature is actually closer to 288 Kelvin. And so we're missing something here, right? What's going on? Why is this? So this is the first sort of hint that we need something. We need to add something to this picture. The other thing I wanted to say is that another question that should make us pause and reflect is that if you take a thermometer and you go on a balloon and you just start going up, then you'd notice that the temperature, this is the temperature of the atmosphere in Celsius degrees, the temperature actually has a weird structure. The temperature will start to decrease until you reach about 10 kilometers, and then it would be constant for a while, and then it would increase again. And then at about 50 kilometers, it would decrease again, and then it would increase again at about 80 kilometers. The section here stops at about 100 kilometers because that's where we think the atmosphere ends. This is known as the Karman Line. And it kind of separates Earth from space, if you will. Okay, but there isn't a real separation. So why is there a thermal structure? Why is it so complicated? Okay, what's going on? Why is the temperature decreasing here? And it kind of made sense why temperature was decreasing here, if you remember from the thermodynamics part. It's just adiabatic ascent. Temperature goes down. In absence of condensation it was G over Cp, right? That was the lapse rate. But why is it increasing in this region that we call the stratosphere? Interesting question. Okay. Obviously, what is missing? Well, this is missing. It's missing the fact that on top of our heads, there is a very thin layer of atmosphere. And to give you an idea of how thin it is, if the Earth was a basketball, the atmosphere would be as thick as would have the same thickness as a credit card. So really, really thin layer. But this is important because it interacts with the radiation. And it, for example, helps trap some of the radiation. It redistributes some of the heat, and so forth. Okay, so it's important that we have the atmosphere, and not only that, it's important that the atmosphere interacts with the radiation. Okay, and this also helps us to explain, for example, why annual mean temperatures are a lot higher than we would expect them to be. They're also kind of uniform, and we'll see also why there is a gradient going from the poles to the equator. Okay, I think we can move on and introduce the main character. And the main character of all the story is radiation. Okay, now, I think you may be tempted to think that radiation is kind of a given. That, yeah, okay, well, it's radiation, and we know how to describe it. But back in the days of the 19th century, radiation was a massive headache for people studying it because, well, for a variety of reasons. One of the first people, actually the first person who, well, okay, let me take a step back. For centuries, for millennia, humans had been exposed to different kinds of phenomena, to electric phenomena. They had been exposed to magnetic phenomena. Ancient Greeks knew how to create some primordial form of electricity. They noticed that if they had a stick made of a particular substance and they rubbed the stick against a wool, then this stick would attract other sticks and they would have some kind of weird interactions that they didn't know quite how to explain. So we were familiar as humanity with these phenomena for a very long time, but it wasn't until the 19th century that we had the tools to start thinking about these phenomena a bit more seriously, a bit more quantitatively, and a bit more mathematically. The Greek philosophers had their own ideas. Aristotle had his own ideas about what electricity was, but the real turning point was when people started using math, right, and using natural science to inquire about these phenomena. One of the major contributions, if not the most important contribution in this kind of realm, was by James Clerk Maxwell in 1861. And Maxwell realized something that was completely non-trivial. He realized that actually the electric and the magnetic fields, the electricity and magnetism were kind of related, which maybe now you think it's obvious because, we all refer to electromagnetic radiation, but for people at the time, they were more or less independent phenomena. There had been some studies by Ampere and other great physicists in the 19th century that had started to show that a magnetic field could generate an electric field in a circuit, and vice versa, that electric phenomena could give rise to magnetic fields. And so there was this idea that the two things were related, but Maxwell wrote four differential equations that I'm reporting here. These are the Maxwell equations in vacuum. And these equations described all of electromagnetic phenomena. Everything that had been derived so far up to that point could be, everything that had been discovered up to that point could be derived in terms of these four equations. And again, I can't stress this enough. It may seem trivial, but it's not trivial at all. And actually, Maxwell discovered that if you started playing with these equations, you would arrive to these two equations. And I don't know how familiar you are with equations, but this is the equation of a wave, and this is the equation of a wave. And you can go on and you can further prove that that these two waves must be kind of perpendicular to each other and move together in what is known as an electromagnetic wave, which is this thing. The velocity of the wave was, is given by this. You know that in the equation, the coefficient in front of this equation is the speed of this of the radiation of the wave. Pardon me. And so Maxwell not only described all this, but Maxwell also gave a way to compute the speed of this wave. And this was interesting because it was very puzzling for people at the time, because the waves that people knew at the time were waves like the sound waves. You may or may not know that sound is a wave. It's a pressure wave that propagates through media. And all these waves were mechanical waves, and they had the property of requiring some kind of a medium to propagate through. These electromagnetic waves seem to describe a lot of phenomena, including light, but it wasn't clear what medium these waves could propagate through. You know, if light is indeed a wave, and this was a long-standing debate in physics, you know, going all the way back to Newton. Newton did not believe that light was a wave, by the way, if I recall correctly. But, you know, if light is indeed a wave, then what is it propagating through? And that is what led to the introduction of a concept of ether. But we will not get into that. So this was all to say that this was a big deal, that people, you know, when this was discovered, this was, you know, it probably still is one of the major results of classical physics, you know, before we turn to quantum mechanics and relativity in the 20th century. This was truly one of the, you know, pinnacles of physics. Okay, so what does this electromagnetic radiation is and look like? Well, like all radiation, it can have different frequencies and different wavelengths, and so, you know, it has a whole spectrum, right? And it also turned out that there is a particular band within the spectrum that correspond where electromagnetic radiation is what we call light. Okay, and the light goes from blue, that is kind of a higher frequency radiation, all the way down to red. Actually, this is not correct. Beyond blue, there's also violet. Okay, and we do perceive violet. We do see violet. Okay, so violet would be one boundary of this spectrum that we can see, and red is the other spectrum, the other boundary of the spectrum that we can see. Anything beyond violet we cannot see, and we usually call this ultraviolet or UV. And this includes X-rays and gamma rays. These are the bad radiation that would kill you, which were not discovered until much later. These were discovered in the 20th century. So people back in Maxwell's time had no idea about that there would be such things as X-rays and gamma rays. But there's also energy. There's also radiation at a lower frequency, and this is called infrared. Okay, infrared is right after the red. We cannot see this, and can keep going down at lower frequencies. You'd have microwave radiation. That's what heats up whatever you cooking every day, and then you have radio waves and kind of radio type waves, and so forth. Okay, so this is quite a spectrum. It has different features, and interestingly, the infrared part. Well, we will be interested in the infrared part, in the ultraviolet part. Okay, this is an interesting part of the spectrum. Okay, this here, if you will, and it is interesting for us because it bears some relevance to the. Sorry, I deleted the wrong one. Anyway, I meant to do this. It's interesting to us because this comprises radiation that we come across in the atmosphere. Radio waves, yeah, we do have radio waves. I mean, we do have radios, but this is not something that is produced by the sun or the clouds. X-rays and gamma rays, very luckily, these are in commons in the atmosphere, because otherwise we'd be dead already. And so this is kind of the region we're interested in. The infrared is usually also divided in different branches, different parts. We have a near infrared, which is very close to the color red, as you can imagine. A thermal infrared. We'll see why this is called thermal infrared, and then far infrared, that is very, very low frequency. Okay, move on. Now, the typical distinction that we make, is between so-called shortwave radiation and long-wave radiation. The reason why that is that we have essentially the radiation that is coming from the sun is pretty high frequency radiation. It's absorbed by, so it's it's ultraviolet radiation. It's absorbed by the Earth, and it's re-emitted at a very, very low frequency, at a much lower frequency than the radiation that came in. So even though radiation is a continuum, and the spectrum is more or less a continuum, what is coming in has a pretty high frequency, and so a short wavelength. What is emitted out has a much lower frequency and a much higher wavelength. And so we talk about short wave radiation, which is what comes in from the sun, and long wave radiation, which is what is emitted from the Earth and goes back to space. Are short wave and long wave radiation kind of emitted, or actually are different frequencies of radiation being emitted with the same intensity by the sun, but also by other objects? The answer is no, and I'm going to show you right now what these look like. Let's just focus on the yellow color here, okay? Or if you will, this shape, this curve here. The red will play an important role later on, but we'll talk about it much, much later. This is what we call spectral irradiance, meaning the intensity of radiation at different frequencies, if you will. And the yellow is what comes in at the top of the atmosphere, okay? Sunlight at the top of the atmosphere. Notice that, first of all, it has a weird shape, and we'll talk about the shape for the rest of this class, more or less. But notice the interesting thing that this shape has a peak at about 550 nanometers, more or less, and then it drops down as we go to shorter wavelength, so higher frequencies, and it drops down as we go to lower frequencies. So interestingly, the spectrum of the solar radiation. So this is all, the sun emits in all frequencies, but it emits in the visible the most, if you will. So it's putting more energy, more power in the visible light, which seems like a big coincidence, right? Like, wow, what a coincidence that we can see exactly, our eyes can see exactly in the frequency band where the sun emits the most, where, you know, the frequency band that is quote unquote the brightest, right? If we could see infrared radiation, so down here, there wouldn't be a lot of radiation that we could see. We would be kind of always in the dark, right? So how lucky that we can see up here and not like here or like here. I mean, is it a coincidence? Well, obviously not. It's most likely a product of evolution, right? I mean, creatures who could see in this band, they had greater advantage because they could see predators and they could spot prey and stuff like that. And so that, it's not a coincidence that we evolved to see within that spectrum. But yeah, so if you were a physicist, you would look at this shape and you'd think, okay, but why this shape? Why not, I don't know, why not a Gaussian shape? Yeah, this is more or less a Gaussian. Why not, like something like this? Why not a constant everywhere? Why this shape? Why something like this? And can we describe this mathematically? This question, as it turns out, was people didn't know it at the time, but this turned out to be one of the most important questions that physicists asked in the 20th century. And this is something that tormented physicists right around that time. Now, let me drink some water. So, near the end of the 19th century, beginning of 20th century, physics knew something about radiation, right? People knew through the Maxwell equations. Also, in case you're wondering, I forgot to say this earlier, Maxwell is the same as the Maxwell-Boltzmann distribution. Yes. And people had a way to determine, people had a way to estimate what this radiance should be, okay? And one of the results that came out was a result by two people, Rayleigh and Jeans. This is known as the Rayleigh-Jean approximation. And what they predicted was that, well, this curve, this irradiance that I just showed you just now, this curve here, well, using Maxwell equations, that curve should go like twice the speed of light times the Boltzmann constant times temperature divided by the fourth power of the wavelength. Okay, now this is wavelength. Okay, and let me just erase what I drew here. Okay, so you can see it better. So let's start from way down here. This curve would be growing like the fourth power of wavelength, and so it would be a really steep parabola-like shape. So it would be something that would go up very rapidly like this and just keep going up and up and up. But notice that something happens as you go towards, oops, this was embarrassing. It grows like 1 over the fourth power of wavelength, sorry. So it comes from high wavelengths and it goes, it starts to increase as the wavelengths decrease and go up and up and up, and it would just keep going. And as the wavelength lambda turns towards 0, because of this formula here, b, so the limit of, for lambda going to 0 of b lambda of t is, well, infinity, which is interesting. So this would just blow up, and it would blow up in the ultraviolet. And so this became known as the ultraviolet catastrophe. Yes, the ultraviolet catastrophe, okay? And so this is a big problem because infinities make absolutely no sense in physics, right? And so people were really desperate. Imagine that you've developed a system of knowledge that can describe every kind of electromagnetic phenomena that you think is out there, and you think that you've made it, that you've discovered all there was to discover, which is what many scientists felt at the time. And then suddenly you try to compute, what would be the curve that you expect for spectral irradiance, and boom, you get infinite, which makes no sense. And whenever you get infinities in physics, it means that there's something fundamentally wrong with your theory, okay? So the person who solved this was this person called Max Planck, which doesn't look like a very happy person. But in spite of his kind of grudgy appearance, he made one of the most important contributions in the 20th century physics. And I think he did it, quote unquote, without realizing it. So what Planck did was that he started playing around with various assumptions, okay? And he determined that if, instead of having this electromagnetic wave, if this electromagnetic wave was broken up in sort of particles, one after the other, something like this, and each particle had a very definite energy that was proportional to the frequency of the wave, and in particular, he called this proportionality constant h, okay? So this would be the energy of each one of this particle. Then he determined that if this was the case, then the ultraviolet catastrophe would be prevented, and the energy, the spectral irradiance of some kind of body emitting radiation would have exactly the shape that had been observed. And it was kind of interesting because Planck, it's not that he didn't believe in it, but it just found it kind of empirically. He was just trying different ways to think about this problem, and it kind of came across this idea, and he gave it a shot, and calculations somehow agreed really, really well. Now, I made it sound like, Planck was this doofus doing things just, without knowing what he was doing. Obviously, Planck was a, tremendous genius, and he realized the consequences of his ideas after he discovered them, but he wasn't guided. What I'm trying to say is that he wasn't guided by, some kind of a knowledge that he had beforehand. And yeah, so he called these particles quanta, a particular amount of energy, so quantum of radiation. And it turned out that they could explain a lot of things. And so a lot of people around the same time started trying to develop a physical theory for these quanta. It's what we now call quantum mechanics. These quanta of radiation is what would later become known as photons. Okay? And photons were used by Einstein, who, by the way, did not believe in quantum mechanics. They were used in 1905 to explain a kind of phenomenon that was known as the photoelectric effect, and that people couldn't explain. And which was also the idea that got Einstein the Nobel Prize. We could talk about why he didn't win the Nobel Prize for relativity, but let's stick to that. Okay, so Planck introduces this idea, and very importantly, let's just think about this. Very importantly, the energy of these quanta of radiation, of these photons, is not proportional to the intensity, but it's proportional to the frequency, which is, if you think about it, very counterintuitive. So you would imagine that just out of experience, you would imagine that intensity would have something to do with it, but instead, Planck says, no, it's just frequency. Okay, so there's another thing that was going on in Copenhagen at the time. In Copenhagen, well, pretty much everywhere in Europe, people were starting to research on people were looking at looking at, how can I say this? People were trying to understand why materials that are heated up emit light, okay? And in particular, people found that if you heat up a gas, for example, very simple gas, and you heat it up to the point that the gas is emitting light, and you pass the light through a prism so that it kind of opens up in a rainbow, what you end up getting is not a rainbow, but is a series of very definite colors, okay? And if you were to put the colors in order according to their frequencies, then you get something very similar to this thing here, okay? This is called a spectrum, if you will, and it's exactly this. I think this is hydrogen. So you take some hydrogen in a bottle, you heat it up. Don't do it because hydrogen is kind of highly explosive. So don't do it, but you heat it up in very controlled settings, and you get a kind of light, and if you pass the light through the prism, then you get all these colors. You order them by frequencies. This is what the colors look like. And notice how these colors have very specific positions. Different atoms have different kinds of positions, different kinds of spectra. So, I mean, why, right? Like you observe something like this, and again, like the physicists would want to say, but why are we observing this? Why are we observing this kind of regularity? First question. First problem, if you will. Second problem is that we know, and people knew at the time, that if you have some kind of a charged object that is accelerating, okay, this charged object emits radiation, okay? Excellent. However, if we think about the atom as, if we think about atoms going around, if we think about atoms having a structure like the solar system, where you have a nucleus at the center and electrons or charged particles going around it, these charged particles, because they are circling around, they are constantly accelerating, right? Because they are going in circles. And so these particles must be emitting radiation all the time. But if they emit radiation, they're losing energy. And if they're losing energy, how can any atom be stable? How can atoms not collapse? Actually, it's a relatively simple calculation. And if you compute it, atoms would be stable for, if I remember correctly, something like 13 minutes, after which atoms would just, they would just collapse. So how come that everything is not collapsing? Well, around the same time, this person called Niels Bohr, he was a lot younger when he did it, he had the idea, very non-trivial idea, of taking the what did I want to say? paper, the result of Planck, and proposed that actually this idea that radiation is quantized and that radiation is quantized can also apply more generally to everything in the microscopic universe. And so he said, if we assume that the atom has indeed a nucleus and some charged particle going around it, which was what people were discovering at the time, okay, then he made a few fundamental assumptions. The first one was that electrons, these charged particles, negatively charged particles called electrons, can be only at particular distances. So they can only occupy a very defined set of orbits, okay? And when they're on these orbits, they do not emit radiation, okay? Then the atoms are stable. And furthermore, electrons can go from one of these orbits to another orbit, okay, with a discrete jump by absorbing one of these quanta of radiation. So there's a quantum of radiation that travels, is absorbed by this electron makes this jump. Vice versa, if an electron jumps from a larger orbit to a closer, lower energy orbits, it will emit a quantum of radiation, okay? And this was the interesting thing, because he said this quantum of radiation will have to have exactly the energy corresponding to the change in energy going from one orbit to the other, okay? We all know that even from classical mechanics, different orbits in a gravitational field, in an electric field, have different energies, okay? And the orbits closer to the nucleus or the sun or whatever have a lower energy. And so even in the quantized atomic model of Niels Bohr, the levels, the electrons in the closer orbits will have a lower energy than the ones at the outer orbits, okay? And so this is completely non-trivial, because now he says, when you do this jump, you will emit a certain energy, or if you want to do it the other way, you will have to absorb a certain energy. And this energy is either the energy that you need from the photon or the energy that you give to the photon when it leaves you. And this energy is equal to constant, Max Planck's constant, and the frequency of this radiation. And so if you think about it, this can explain why, when you look at the spectrum of hydrogen and of any other atom, why you have these very discrete shapes. Each one of these lights is given by photons that correspond to a jump from one orbit to another. And the reason why there is no continuum is because there's no continuum in trajectories, in orbits. So, the orbit, this is one orbit, this is another orbit. These are always the same, and they've always been the same since the beginning of the universe. This jump in energy corresponds to a frequency that is, let's say, this frequency here. The outer, this jump in energy has, we'll call this nu 1, this we call nu 2. This new jump in energy corresponds to this here. And so when you have, and so forth, nu 3, nu 4, etc. So when you have a gas, you have billions and billions and billions of molecules, you'd have, these processes are happening all the time, electrons jumping up and down from one orbit to another, and therefore you have a lot of photons that are emitted, but the photons have always the same frequency, and it's the frequency that corresponds, pair Planck's relationship, exactly to the differences in energies of the orbits. I hope this is clear. It's a little bit counterintuitive maybe, but also another important thing to keep in mind, if you need an energy to go from here to here, you need a certain delta E, okay? And suppose that there's a photon flying by and the photon has energy delta E plus epsilon. The electron cannot absorb part of it, cannot absorb the delta E and throw out the epsilon. The photon will do nothing to the electron. So the photons must have exactly the right frequency in order to excite the electron to jump from one orbit to the other. Okay. Also, just to fix the notation, orbit was the term that was introduced at the beginning. People realized, for all kinds of reasons that we don't want to go through, that a better word was orbital. Orbital. And this is what we'll be using, okay? We will talk about this, and we'll talk about this later because it will be important for the atmosphere. But essentially, atoms can, they have electrons and they can absorb photons, and the electrons jump from one orbital to another. However, remember that atoms can also have a charge, can also form bonds, right? You can have a nitrogen atom and another nitrogen atom, and they can form some kind of a bond, okay? Same goes with oxygen, or oxygen and two hydrogen atoms, you can form water, okay? A water molecule. Now, these bonds are characterized by particular kinds of energy, and also these molecules can also have degrees of freedom, okay? And in particular, as you could imagine, these bonds are not, even though I drew it with these lines, these two atoms are not joined by a physical stick, right? And so they can move around. And in particular, the molecules can oscillate around some kind of an equilibrium point, and they can vibrate, if you will. Okay. And if you give this system some energy, it will vibrate in a certain way. If you give it more energy, it can vibrate in a different way. Okay. Another thing that could happen is that this thing could also rotate, right? It could rotate around. And much like you're probably starting to realize that a lot of things are probably quantized, meaning that they're divided in very discrete forms. And so much like the orbitals are discrete, there's one here, but none in between. Also, the ways of molecules to rotate are also kind of discrete. Can rotate with only specific kinds of frequencies. And so not only atoms absorb photons, but also molecules absorb photons. And this absorption can make them vibrate, can make them rotate, can also break them apart. If the photon has the right energy, then boom, this bond will be broken in two, and so forth, okay? It turns out this will play a very important role in understanding why the atmosphere behaves the way it does. Another interesting process that can happen in the atmosphere is a process known as scattering. Okay, scattering is a process by which a particle or some electromagnetic radiation deviates from its path. Okay, and scattering can kind of be understood in a classical way and can also be understood in a quantum way. But you could you could imagine, let's say that there's an atom here. There's some radiation impacting the atom. The radiation is absorbed and it's re-emitted with a different angle. That's scattering, okay? And the angle with which it's deviated, this is known as the scattering angle. There are two different limits and two kinds of scattering that we will talk about because scattering is important. The first type of scattering is called Rayleigh scattering. And this happens when the photons is a lot, when the particle that deviates the course of radiation is a lot smaller than the wavelength of radiation. So when you have radiation that looks like this and the particle is really just a tiny little point, okay, that absorbs and re-emits, that is Rayleigh scattering. There's also Mie scattering. Mie scattering is when you have radiation, but when the particle has a similar size to the wavelength, okay? The other limit is where the particle is gigantic, okay? And that is just optics, essentially. So do we know, is there any example of Rayleigh scattering in our lives? You know, do these things play any kind of role? Do Rayleigh scattering and Mie scattering playing some kind of a role in our lives? Well, yeah. Rayleigh scattering is the reason why the sky is blue, and Mie scattering is the reason why clouds are white. This we'll talk about more in greater detail in a couple of lectures, but just wanted to sort of give you a heads up that these are important processes. Okay. Okay. So just wanted to introduce some definitions that we will be using. The first definition is that of an isothermal cavity. And this is important because it played an important role in in conceptualizing quantum mechanics, if you will, and in thinking about radiation. An isothermal cavity, as the name suggests, is simply a cavity where the walls are maintained at a uniform temperature. Okay, very simple. Now, thermodynamic equilibrium, this is something we talked about, but just as a refresher, in particular, thermodynamic equilibrium applied to our discussion is an equilibrium where the tendency of radiation where the radiation that is emitted by the atoms in the cavity equal the absorption. Okay, we saw some kind of equilibrium when we talked about a liquid and a gas, and we said when we have enough material, enough molecules, when we have, the same rate of molecules leaving liquid for gas as the same going from gas to liquid, we are in equilibrium. In this case, we have an isothermal cavity. We are shining radiation in it. Radiation will interact with the atoms on the wall of the cavity. Okay. The atoms on this wall will absorb some radiation, and then that will re-emit it. In a condition where the emission rates equal the absorption rates, we will talk about thermodynamic equilibrium. Okay. We will also assume generally that the radiation is isotropic, meaning that it's the same in all three directions, x, y, and z. Okay. Another very important definition is that of a black body. A black body is a body that absorbs all the radiation that is thrown at it. Okay. Is everything a black body? Well, no. Just look around yourself. If things have a color, then it means that they're not absorbing radiation corresponding to that particular color. If you have a blue book, it means that the substance that is covering that book does not absorb blue, and it's re-emitting it and that's why you see it. One way to conceptualize black bodies, or to think about black bodies, is if you take an isothermal cavity, if you take literally a box, and you make a really small hole in this box, and this hole it lets radiation come through, but then radiation kind of starts bouncing off the walls and never leaves the cavity, okay, this cavity, okay? And so all the radiation that is thrown at this is absorbed because it never leaves, okay? Well, spectral radiance is the power that is emitted in radiation per unit area, per unit solid angle, and per unit frequency. This is something that we'll talk about later on. Do black bodies exist? Well, this is an excellent question. Black bodies are an idealization. Most things, if you see them, they're not black bodies. Just, by definition, right? We see light that is reflected off of something, right? We don't see the object, we see the light that is reflected off of that object. If you can see that object, it means that that object is reflecting some of the light. And that means that object is not absorbing all the light, all the radiation that is thrown at it, okay? People have developed a kind of color, have engineered a kind of color that absorbs a lot of radiation. That black is, it has to be a black, right? That black is known as Vanta black, and it's what is shown here in the picture. It really looks like a hole, and so it's kind of it looks kind of promising. Still, it's not perfect, of course, but that is kind of an idealization, and that is a way to conceptualize, to visualize it, and to realize it. In the universe, you might think, given that black body has a similar name to black hole, you might think that black holes are black bodies. Well, yes and no. Black bodies are a good approximation to black holes are a good approximation to black bodies, but it turns out that black holes actually emit some radiation, even faintly, but they emit some radiation. This was one of the discoveries of Stephen Hawking, maybe one of his most famous, I don't know. But so because of Hawking's radiation, black holes are not exactly black bodies, but close to it. More generally, we speak of a gray body or gray bodies, okay? So meaning that a body absorbs some of the radiation, but not all. Okay, so let's just go back to a little bit of math. We talked about Max Planck, right? And we talked about how Max Planck resolved the paradox that was the ultraviolet catastrophe. Okay, so Planck's result was to obtain a formula for either the spectral power, which is what I had shown before, or the spectral energy density, which are very similar, if you will. What we call Planck's law is a law that says that the spectral energy density, so energy divided by the volume, of a black body radiation at a certain temperature T is given by this formula here. Okay. Notice that there's still KBT, so our good friend KBT is still here, just to remind everybody that whenever you have a temperature, chances are that there's always a KB to turn that into an energy. And these two are kind of, it's an energy over an energy. Sort of radiative energy and thermal energy, if you will, in a way. And the spectral power that is related, the spectral power that is transferred by a group of photons in a particular direction, is given by these two functions. Okay, this one is function of temperature and frequency. This function of temperature and wavelength. Now look at these two functions. Do these two look familiar to you? Like, have we seen them before? Question mark. Well, if you paid attention a few slides ago, if you paid attention to the numerators, these look a lot similar to, they look a lot similar to these two guys here. Okay, and in fact, if you take this and you go in the limit of large lambda or small nu, okay, you can show that these functions become exactly the Rayleigh-Jean approximation. Okay, so in a way, Planck improved on Rayleigh-Jean by using a completely different theory, but it's interesting that there is a limit at large enough frequencies where the two things are actually merging into one another. Much in the same way that you could use classical physics to say something about the hydrogen atom, okay? And quantum mechanics couldn't be more different from classical physics. It's actually a complete revolution. But if you take quantum mechanics and you bring it at low energy, you take it to low energies, then quantum mechanics kind of flows into classical physics, which is really the beauty of this, because you need to justify the fact that the old theory was doing a good enough job. It wasn't perfect, but it was doing a good enough job. And everyone would want a final theory that explains everything. But the fact of the matter, and maybe you think that quantum mechanics is that theory, but the fact of the matter is that that's not true. That quantum mechanics has its own limitations, and there are calculations people discovered in following decades. People discovered that there are some calculations that if you attempt to do them with quantum mechanics, the answer you get is infinite. Okay. Another thing that another thing that we mentioned before, it was the Stefan Boltzmann law. People had observed in the 19th century that the spectral power, so the power that is emitted by some body, including all the wavelengths, that spectral power was proportional to the fourth power of temperature. Okay, and so Stefan and Boltzmann said this spectral power over all the frequencies, that is some constant times t to the fourth. Okay. Where did this come from? Well, Stefan and Boltzmann said, well, we don't know. I mean, that's what it is. That's what we noticed, and this is the law. But the beauty of Planck's result is that now you can go and take b lambda, the spectral power for each frequency or for each wavelength. If you integrate it over the wavelength, you obtain exactly Stefan Boltzmann law. So you know that you tapped into something profound when you can explain other things that were not explainable before. Okay, so Stefan Boltzmann's law suddenly becomes clear, becomes obvious why that is. Another thing that people had noticed, and this is something that people had known for at least a good decade, since 1893, was a law called Wien's law. Wien's law says that if you have a black body, that emits radiation at different temperatures, the peak at different temperatures, the peak of the spectral energy density is reached at lower wavelengths the higher the temperature. Okay, so in other words, lambda, where maximum, goes like 1 over t. And this now became obvious considering Planck's result. Okay, how do we compute that? Well, you have B of lambda, and B of lambda describes the shape of these things. You want to know where the peak is, so just do this, right? And you obtain something like this. And not only that, but you can also compute the proportionality constant. Another important law is known as Kirchhoff's law. And yes, this is the same Kirchhoff's as the guy for the electric circuits. And also we saw Kirchhoff's relations when we talked about phase transitions. And yeah, it's the same Kirchhoff. We introduced two concepts. The first concept is that of the spectral emittance. This is the ratio of spectral radiance from a given body to the spectral radiance of a black body at the same temperature. Okay. Spectral absorbance is the same but for absorption. Okay. So it's a fraction of the energy falling into a body that is absorbed. Okay. Kirchhoff's law simply says that these two things are the same. Okay, and this is something that will be important later on. Okay, so we talked about thermodynamic equilibrium before, and we talked about, if you remember, at the beginning of the thermodynamics part, we talked about the Maxwell-Boltzmann distribution, right? And we said, well, if you have a gas, suppose that you have a box, you have molecules in this gas, and these molecules have some energies, right? And these molecules go around and travel with some velocities, and we had determined the probability distribution for a given speed, which also corresponds to different energies, different kinetic energies to these particles. So now we have the possibility of adding radiation to the system. Or if you will, looking at this from the other point of view, think about the spectral the isothermal cavity that we had before. Now we're introducing a gas into this cavity, and gas is complicating things. Because before we had radiation interacting with the walls of the cavity, but now we also have the gas. And these atoms can absorb the radiation. So one question that you might think of is, we know that in the absence of radiation, molecules are going to take the Maxwell-Boltzmann distribution of speeds. Are we going to affect, is the radiation going to affect, Maxwell-Boltzmann distribution? Well, it turns out that if you do all the calculation, then you can show that there are two regimes. Okay, one regime where the ratio between the probability of transition by collision to that by radiation is really, really high. So a regime where collisions are super frequent, okay, and really effective at making you change direction and making you change speed. But there is another, and so in that regime, you could think of that as a regime in which radiation can be kind of ignored, or it plays a smaller role, okay? When that happens, we talk about a local thermodynamic equilibrium, okay? And this kind of happens in the atmosphere near the surface. At the bottom, 50, 60, 70 kilometers, the gas is so dense that many, many collisions happen, and therefore local thermodynamic equilibrium holds. But as you go higher up in the thermosphere, the density is so low that the chance of colliding with other particles becomes really, really small. And so radiation, you could expect radiation to play a much, much bigger role in that region. And so over there, radiation plays a much bigger role than collisions. Okay, this concludes the first set of things that I wanted to tell you. I hope this wasn't too confusing. I hope it was clear. It's a bit of a shift in gears from microphysics, but yeah, I hope it was clear enough. As usual, if you have any kind of questions, just let me know. Feel free to email me or text me. Otherwise, I will see you next time for the next lecture on radiation.